So what you have here is typically electric dipole interfering or interacting with either magnetic dipole or electric quadrupole, which enter into the same order of the perturbative expansion. It turns out if you're talking about an isotropic sample, which gases and solutions are, that quadrupole term averages out to 0. However, predictions are that actually that quadrupole term might actually be a bigger effect if you could hold the molecule stationary and do a measurement on a stationary molecule. But I would say that as chemists and as spectroscopists, we don't have a good handle on magnetic dipoles because we really haven't studied them a lot, because they are typically so weak that you don't see them. But here is an example of something where you need to have the presence of those higher order terms. Without those higher order terms, they would not exist. So we do not have a good handle at all.
John Doyle does experiments with
Microwave.
right, and basically it doesn't have anything to do with the magnetic.
Because it's three-wave mixing.
That's right.
My other
he is criticized a lot because
not by me.
No, but because since it's a microwave experiment, it has to be on the gas phase. He can't do any condensed phase experiments. And so everybody takes his measurements, which are extremely sensitive and extremely accurate, and says, well, so what? We're not good. This is not relevant to chemistry.
I would disagree.
Well,
now, first of all, I want to point one thing out. He does get a chiral signature, but he cannot relate at present, and I know I've talked to Kevin and folks paid about this, they cannot relate the sign to the sign of their response. I mean, for a given molecule, they get a positive FID phase. For another molecule, they get a negative FID phase, but they cannot predict which one they're going to get, right? Because there's some strange, miscounting of phase in the microwave scheme.
Yeah, my understanding is it's all experimental.
No, I believe that's the case. I believe that's the case. But certainly, most practicing chiral-optical spectroscopies are using techniques that are done in the solution phase. And they're typically doing maybe ECD, electronic circular dichroism, VCD, vibrational circular dichroism, ORD, okay? And there is no doubt that the things that Doyle and Patterson did are, in my opinion, the first advance in chiral-optical spectroscopy in the past 40 years. The first new way to detect. It is going to be useful as an analytical tool by looking at the effluent from a gas chromatographic column. But it's not going to be something that can be used easily in production chemistry. I think it's important.
So, a couple of things.
Okay.
One is just that I'm just trying to just sort of visualize the role that the solid actually playing here, right? And first of all, I guess I'd say it's not surprising that big polarizabilities matter of the molecule too.
Yep.
Because ultimately what we're talking about is you're applying an optical field.
Sure.
And it's distorting the electron in a way that twists it and moves it upward, forward, and back.
Yep.
So it has to at least have a reasonable magnitude.
Mm-hmm.
And the best I can imagine for what's happening with the solvent, that if it's really the polarizability that matters, is that basically the charge distribution of the solvent is simply being dragged along as well.
Yeah.
Yeah.
To a good extent.
Yeah. It's just
Although,
contributing to the rotation
but
because the electrons on it also are getting moved in the same sort of way.
To an extent. I mean, there are people who have different ideas. I mean, some people believe, well, can I go back to?
Sorry, once you pass, we don't allow it. The bylaws of the MOS.
Okay.
It's Ram Chandra, he insisted on it.
He's not here.
Yeah.
So if we go back to this, this is crazy, right? This is wild.
But this is what, that's right, because the salt, well, yeah, this is what made me think that, okay.
No, but there's more here than just that. I I didn't say it, but let's talk about it. And what I'm about to say is coming purely from calculations. Right? If you look at the outliers here, so here you have benzene, okay, and that really is far away from everything else. What's going on? Calculations are indicating that this curve has nothing to do with the methyloxyrane itself. It is actually a chiral cage that has been carved out into the benzene solvent. It turns out benzene has weak electronic systems in this region. And so what you're seeing, and this is coming from a calculation, no experiment to verify this. It's come, and that chiral cage is giving you the response. If on the other hand, we look at this one here, and this one has even perhaps less evidence behind it because there are experiments that say it's probably wrong. Okay. But from calculations, it's believed that, again, this has nothing to do with the bare methyloxyrate or propylene oxide. It has to do with a binary complex form, which is giving you that. Although there are microwave experiments that would say it. So, you know, for these outliers here, there certainly are complications. But I can believe for the middle set here, there certainly is an intimate coupling of electron density or whatever you want, however you want to term it, between the solute and the solid.
Yeah, in this respect, I don't think that the solvent effects on things like dephasing times matter, as long as you're off resonance, so that there's no one transition. Or, for that matter, I wouldn't think about it in terms of the time scale of a response, as long as you're off resonance.
It depends how far off resonance you are, right?
Okay, sure, but, yeah, sure.
I mean, because you have you know, the dephasing
No, of
could
course,
be
it's
very
not
big.
to matter as you
Yeah,
approach
yeah.
it. Yeah. Great.
I think we have no further questions. Let us
Okay. Thank you.